Check, check, check. Hello, hello, hello. Hey, everybody. Just getting this thing set up. Looks pretty good. Hopefully my computer won't overheat and die today. We'll find out. But we'll start in about 4 minutes, and we're talking about data science. Today we're actually going to talk about things that maybe not data science, but still towards high school math. And almost all the things that we're going to be talking about are basically unreleased. So things that we've not created YouTube videos for, stuff that you haven't really seen yet, but that we put a lot of work in. And it's not that they aren't good. It's we just haven't had time to do YouTube videos for it yet, and very happy to share that with you today. I'm going to close Discord if I don't mind, so I don't get Discord messages on the thing. I'm going to tell Scott and Julie that I'm streaming now. Okay. Alright, so we'll start again and start in about 3 minutes. I have entirely too many tabs open. Just gotta make sure, as long as I don't close that tab, I should be fine. Alright. So let's see. There we go. Okay. The sound is good. All right, fantastic. So I'll talk about this as well when I get a chance. I probably should have put that into the into the live stream. I don't know if I can. Can I edit the? OSU. The next one is. There we go. So hopefully that will allow you to see these links here. You can just go ahead and click on them here. But again, the evolution of the STEM coding project is that we started doing a lot of activities for physics, interspersed with other things. We started off doing a lot of stuff for physics and physical science, and that was a lot of fun. And then we did, but even in 2017 we were doing stuff for math, and so this is not like totally new that we're doing stuff for math. So we started building fun stuff for math, like Pi Day, so I'll talk about Pi Day some today. And then at some point we got really excited about data science, so there was free economics, data science, here we go. I think is it this one? Yeah. Yeah, so I'll talk about this in a second, but this was kind of a turning point in the discussion around high school math, essentially. But anyway, we'll start in a minute, and feel free to add any questions in the chat that you like. Feel free to join our Discord server. We are probably not going to advertise the Discord server as much after these live streams. Today is actually the last live stream for a while, and so please join the Discord now if you like. The Discord is kind of intended for teachers and educators, so if you're doing after-school programs, you're still an educator, and we'd still love to chat with you. But you know, if you want to contribute, you want to help us build stuff, you want to, you know, lend your skills. If you're not an educator but you want to help in some way, that's please join our Discord for all those reasons. So, all right, so it's 12 o'clock Eastern Time. Today we're going to continue talking about stuff that we've made for high school math. Officially, this is the high school data science, but in America, data science is most often taught by a high school math teacher. Do you know why science teachers can't teach data science? I don't know either, but that's just how the world works. Sorry, but I'd love it if more science teachers could teach data science, but this is just what we've got right now. So the STEM coding project started in 2017. We started building physics of video games activities, but also in that year we did like a Pi Day activity, we did Earth Day. So we've been thinking about math for a long time. And then in 2019, this podcast episode came out. And this is not a perfect episode. I'm not like endorsing this every word of this episode. But the point is that a lot of people listened to it and a lot of people got really excited about data science because this episode starts off with the premise that complaining about Algebra 2, essentially. I'm a physicist, so there's stuff in Algebra 2 that I like, but I get it. And they greatly highlight a program led by UCLA in Los Angeles, working with Los Angeles Public Schools to do more data analysis in high school math classes. And just practically everybody in education listen to this podcast, and just the interest in high school data science education has been through the roof. We listened to it. We were already doing data science. We did Earth Day in 2017. But this encouraged us to move more in that direction, and so that's part of why we're here. So anyway, so you might want to check that out when you get a chance. So today, we've been talking a lot about data science stuff. The stuff I'm going to talk about today is a little bit on the edge between data science and just regular high school level math, high school level algebra, that sort of thing, trigonometry. So that's what we're going to talk about in a minute. I want to say one more thing before we jump to that, which is that this tab is that we are friends with the people at SIAM. So SIAM is the Society for Industrial and Applied Mathematics. Yeah, so a program of SIAM there. We're friends with these folks. I've presented at SIAM conferences on my plasma physics research. Julie Butler teaches data science at University of Mount Union, and so Scott Zimmerman is a mathematician. So we're friends with these folks, and every year they have what's called the Math Modeling Challenge, in which they release a data set, and then they challenge students to use whatever methods that they want to do to try to understand the trends in that data set and make predictions and that sort of thing. So I believe the most recent one had to do with affordable housing, but there's been other data sets there, so like they have like the challenge, right? And we've thought about doing, revisiting some of the earlier challenges, some of the earlier data. We've thought about doing this for the YouTube channel, so if that's what you want to see, we'd love for you to encourage us to do that. But the main thing is that we encourage you all to think about participating in the upcoming year's events. And so if you're a teacher, that's great, and you want to connect this to your school. If you're not a teacher, it might be possible to partner with a school and start an after-school program that preps students for this. So, so please consider this. This is one of the biggest, distributed kind of data science-y high school things that is out there, and so we really encourage you to check it out. Yeah, absolutely. The other thing I'll say, it's sponsored by MathWorks, and I just want to say, I have a lot of MATLAB in my PhD thesis, so MathWorks gets a thumbs up for me. So that's the other thing I'll say about this event. So I think it's great that they sponsor something like this. Okay, so that's enough for the announcements. Well, one more announcement, which is that tomorrow, Friday at noon, instead of a live stream, so no more live streams for a while because we got to get ready for our classes. Instead of a live stream, Friday this week, which is tomorrow, the 26th, at noon Eastern Time, we are going to have a meeting for teachers and educators on Google Meet, and if you join the Discord, you can see the connection info for that. And we're just trying to, there isn't really a big agenda for that meeting. It's about you telling us what you're thinking about going into the next year, things that we could build, things that we could tweak, activities we made that you'd love it if it could be some different way, videos you'd like to see, anything. So just please join us on Friday, tomorrow at noon. So that'll be a face-to-face. It's not just going to be me talking up here on YouTube where I can't really so much see what you are. So it's going to be a face-to-face meeting. All the cameras are going to be on. I'm going to be there. Scott Zimmerman's going to be there. I think Julie Butler will be able to be there. So we've got an all-star team to be there to listen to what's on your mind. We usually do this every year, actually. So this is not new to us. We usually do this every year around this time. So please take advantage of that. All right. So the main thing I'm going to be doing today, the main stuff we're going to be talking about, is at this link, and the short link for that is go.osc.edu/math_coding, like that. So that's the short link, and then it evaluates to this longer link. So that link is in the description of the page here, so you can check that out. And this is just, normally I send folks to the physics stuff, but this is a page just for the math stuff. There's a little bit of overlap, so like I have Night Sky Simulator here as well. Earth Day is already here, but that's what we have. So we have all these different activities, and I'm mainly going to highlight Pi Day stuff for today, and talk about laser defense. And there's a nice video, and I don't know if I'll have time to do this, but there's a nice video there, and yeah, so this is also a fun one too. So we just have a lot of fun stuff for high school math that we can talk about. All right, so let's jump into it. So if you told me that I could run a high school math class for 1 hour and I had to choose one thing to do with them, like one activity, it's an easy answer for me. It's the Pi Day activity, right? And so we have a nice YouTube video for this, and the basic idea of it is that you've got a square and a circle, and you are using a random number generator to generate all the points for this thing. And initially the points are just kind of all over the place, right? But then you have to use some conditional logic to figure out how many of the points are in the circle compared to the total points, because all the points are in the square, but only a certain number of them are within the circle. And if you think about the ratio between a circle and a square, that ratio would be pi over 4. So it's roughly 3 over 4, right? So 3/4 of the points should be within the circle and the square, right? Whereas maybe only 1/4 of the particles roughly would be in these edges. And so if you get a really precise measurement of the ratio of these things, you can take that ratio and multiply by 4, and it should give you a rough estimate for pi. This is not the world's best way of estimating pi by any stretch. If you're trying to get pi to 1 trillion digits, this is a really bad idea. But the nice part about it is that you can use Pythagorean theorem, that sort of a thing, to figure it out. So what you do is there's an if statement you can add to your code, and we don't tell you exactly what's going on here, but basically you say if the Pythagorean theorem, square root of x squared plus y squared, right? So that for each little point that's here that has some x value and some y value, right? So the distance between that point and the origin is the square root of x squared plus y squared, right? And so if that square root is larger than the radius of the circle, larger than L over 2 basically, or if L is the length of the square, right, then you're probably out in one of these corners, right? If it's smaller than that, then clearly you're within the circle. And so there's some code there to make it light up in a certain way. In the default code, we have it lighting up as gray. So it's actually a little bit hard to see, but there's some gray points here and there's black points here. We did that because some people are colorblind, and one of the options in this activity is to change the colors, which you can easily do at the beginning of the program. But as this thing goes on, you can see more distinctly that there's a circle and a square, and as it goes on, it gets better and better at estimating pi. So then you add to your code, you keep track of the number of points that are in the circle compared to the total number of points, and you take that ratio, multiply by 4, and then that will give you the digits of pi. I'm going quickly through this because we have an excellent video by one of my favorite student hosts. So if you look at if you go digging in the videos, you can find the Pi Day with Kat, and it's in here somewhere. But she has a really excellent video. There it is. Yeah, so there he is. Oh, I just saw it and it went down. So yeah, so you can check that out. So she did a great job on her video. So I don't want to steal her thunder necessarily. Okay, so that's the Pi Day activity. Little known fact that there's a Pi Day Part 2 activity, and I'm going to come back to that one in just a minute. That one has some trigonometry in it. If your students like the Pi Day, there's another thing that you can do, which is Pi Day and Parallel, which is very similar to this one. So, and the premise of this, and maybe this is data science, maybe it's not, but in any case, it's math appropriate, and it's got good geometry in it. So a rewriting of some of the code from the last one. I know this looks a bit imposing here, but if you open up the code that we have here, and this is going to blow your mind, what I'm going to do with this code. This is unlike any other code that is on our YouTube channel, because it is using the multiple cores of your processor to actually accelerate the calculations. Like, amazing. None of the other activities are using multiple cores like this. So this is pretty cool. So there's some code here that is not so easy to read, but this part is somewhat reasonable. Okay, so we're generating random x values and y values, right? That can be anywhere within some square. So this is very similar to what the Pi Day activity I just showed you. You calculate the distance from each point from where it is to the origin of the circle. Normally you do a square root here, but instead this is basically r squared instead of r, which is fine. So if r squared is less than radius times radius, well then clearly you're inscribed within the circle. Whoops, inscribed within the circle, right? And so then you count that as being part of the circle, and then you take that, and then at some point you will multiply it by 4 in order to get an estimate of pi, right? So there's so many things about this code that I love, but maybe it's a little bit, it's a little bit more advanced than the regular Pi Day. Maybe this is more for a computer science class. It's up to you. But basically, the idea is that instead of doing 10,000 points, we're going to do, how many is that? I can't even count. Is that 100 million points? And because I'm running a live stream right now, I'm actually going to decrease the number. So look at my processor here. My processor is in blue, right? Maybe I'll expand that. See if it'll let me expand that. And I'm on Linux, but this works across any operating system. Is it coming up? There we go. All right, so my CPU is doing this thing. right? So my CPU, now bear in mind that this is all like, yeah, so I have 8 different cores here, and they're all, looks like all the cores are sort of like half occupied right now. So what I'm going to do is I'm actually going to use 2 cores. I don't want to use 4. I probably could use 4 and it'd be fine, but I don't want to kill the live stream. So I'm going to use 2 cores here, and then I'm going to run this thing. And let me move this over here so you can see it. So I'm going to run this thing, and then we're going to see it calculate the digits of pi. All right, so I've got 2 cores. And yeah, do you see how it went up, and it came back down? So there was 2 cores there actually that went up. So you can, these 8 lines are for my 8 different cores on my CPU. I have an Intel i7, I think. So 2 of those cores were doing stuff, and then it finished, and then it tells me that the estimate of pi is 3.1417126. So in reality, pi is 3.14152, and so we're a little off, right? But in principle, I could increase the number of points that it's making. So let me increase that by 10, and we'll see it. We'll see if I crash the live stream this time. So I'm going to break the internet. Here we go. All right, so I'm going to do, this should, yeah, let's see what happens. All right, here we go. All right, so it's up there. You got, yep, they're doing it. They're doing it. Let's see. Still thinking. I increased the number of points by a factor of 10, so it's going to take 10 times longer now, right? So I'm not real surprised that this is what's happening. So like, yeah, a lot of these cores are now 100%. Okay, and now it's done, and now it's 3.1416. So that's a little bit closer, right? Because the right answer is 3.1415, right? And so we were at 3.1417, and now we're at 3.1416. So that's slightly better than we did, and it took 30 seconds to do that. And so you can increase the number of points. And what's cool about it, though, is that if you're not doing a live stream, I could increase the number of workers to 8 and just have all my CPUs doing pi calculations. And so I could increase that with another 0, but then also increase the number of CPUs. And you can do these tests on, oh, that's interesting, my network here, history there. So you can do these tests on, you know, if I double the number of cores that I'm using, so workers is similar, if not the same as cores, by the way. If I double the number of cores, so for example, if I went 2 to 4, then it should drop the number of the time of the calculation by a factor of 2, right? So for example, if I reduce the number of cores from 2 to 1, then it should take about 60 seconds, right? So these are the kinds of games that you can play. So I'm going to go ahead and do that. So this one, 2 cores were 30 seconds. 1 core, let's see if that takes a minute. But this is the kind of things that you can do. We actually have, if you ask us on the Discord, we have solutions in which we've run these calculations on like 8 different CPUs to see you know, at how many workers does it stop? Does it like begin to slow down? Does it make sense? So like I have 8 cores in my CPU, but once you get to maybe like 7, using 7 of those, like the speed increase for using 8 isn't that much, and maybe that's partly to do with the 8th core is the one that's running the whole operating system. So so this gets into parallel computing. It gets into weak scaling versus strong scaling, that sort of a thing, which is kind of more computer science, but parallel computing is why the internet works at all, for sure. Like, if you couldn't have these little cores in each processor talking to the other cores to accomplish calculations, then you would not have live streaming, you would not have ChatGPT, you would not have all these great things. All right, let's see how this turns out. So I predicted it was going to take 60 seconds. If I did one core instead of two, it took 57 seconds. All right. So about the similar result, 3.1416. Again, we're expecting 3.15. Excuse me. But this is the kind of cool stuff that you can do. So this is PyDay Part 2. It exists here. It also exists on the stem coding Heroku app thing that we've talked about. Works fine on both those things. And it surprises me that more people don't take advantage of this thing called JavaScript web workers. It surprises me that you do not see more people in computer science education using this to teach parallel computing. Because without this, you have to install stuff on your computers, and it's an enormous headache. But I didn't install anything. I just opened P5.js. This is built. This is not even a library that I'm loading in. This is built into JavaScript. So I think more people should take advantage of this sort of a thing. All right, so that's PyDay and Parallel. And yeah, another cool part about that is that as you increase the number, like maybe you don't know how many cores are on your CPU, right? Maybe you think your CPU has 4 cores, but for all you know, it has 8, right? So what you can do is you can keep increasing the number of workers, and that can tell you how many cores it has. And that seems like something that wouldn't happen, but some CPUs now, and like my iPad, for example, some CPUs, they have like fast cores and then like slow cores. Why they do that, I have no idea. But you might have 6 fast cores and 2 slow cores, and you don't know, well, does that mean that I have 8 cores that can speed things up? Like, you can figure that out. Like, you can figure out effectively how many cores you have. Or like hyperthreading. All right, so suppose my CPU is hyperthreaded, but like according to this thing, how many cores can it actually take advantage of, you know? So that's the cool part about the activity is that, or maybe, you know, one of the challenges on this thing is like if your students have an Xbox, go home to the Xbox, run this thing and see how many cores see how many web workers does the calculation no longer speed up. So it's just a fun thing to think about what your devices are doing and how things are running. So PyDay Part 2, this has some trigonometry in it, and so, you know, maybe you're teaching a class that has trig, maybe you don't. But the premise of this is, and really the premise of PyDay and Parallel, is that the first PyDay is actually a pretty terrible way of calculating pi. Like if you watch the video with Kat, they're just sitting there and watching this thing, and it takes forever to get to 3.14 in the way that they're doing it. Like using random number generators to estimate pi, it works, but it's not efficient at all. Like this is not how people get out to trillions of digits of pi. And it's pedagogically useful and straightforward, but by the way, it's referred to as a Monte Carlo method. But it's not a great way to get the digits of pi to many digits. A better way to do it is the way that people actually do it. It tends to be more of these series that they add up. And so the simplest, a relatively simple series that allows you to figure that out has to do with this triangle. So this is a right triangle, so the corners have 45 degrees in them. And basically, if you've heard of SOHCAHTOA, right? So sine is opposite over hypotenuse, right? So SOA, right? So CAHTOA, so CAH, cosine is adjacent over hypotenuse. TOA, so tangent is opposite over adjacent. And so in this triangle, tangent theta is going to be the opposite divided by the adjacent, which is 1. So tangent theta is going to be equal to 1, which means that the inverse tangent of theta should be 45 degrees. Well, that's fine. How do you get to pi from there? Well, 45 degrees, if you think about it in terms of radians, right? So there's 2 pi and 360 degrees, right? And if you think about it carefully, you'll realize that 45 degrees is actually pi divided by 4. And so if you have a way, so another way to estimate pi is that instead of using a random number generator, if you can somehow estimate the inverse tangent of 1, then that gives you pi over 4. You can multiply that by 4 to get pi. And so this is kind of a weird stem coding activity in the sense that we're doing a series. Like it's written differently than a lot of the other things. But this is the expansion for arctan, which I just sort of give you. Exactly how you would calculate that is something to ask a pre-calculus or a calculus teacher how to do. But if I just give you that, and you just keep adding the terms, eventually you'll get a pretty decent estimate for pi by multiplying pi by 4. When I was in graduate school, I would sometimes see in scientific codes, at the beginning of the code, it would say pi equals 4 arctan 1. I was like, what is that? And then I realized one day, I was like, oh, well, it's just pi over 4 times 4. Of course. Because if they don't want to just save the value of pi in the program, they can just calculate it like that. So anyway, so this is, if you're teaching maybe a pre-calculus course, this might be a fun one to do. And it is graphical. Like it actually does, you can kind of see it. So that's, what was that doing? So at the end it's going to look something like this. So as you include more and more terms, this is like 22nd, 30 terms or something like that, you are getting closer and closer and closer to the true value of pi. You can see the error going down. So there's something fun to watch. Like that's my complaint with series, right? There's not always something fun to see. So if the stem coding activity, so there's got to be something fun to look at. So that's part of the premise of that activity. So there you go. So that's Pi Day part 2. One of these days we're going to make a video for it, but until then you can find it there. Definitely check out Hidden Figures. So circular orbit is very straightforward. So Jamar was in that video. We haven't had time to do a video for the re-entry one. This one is a little bit more advanced. I'm very proud of those two. All right, let's talk about laser defense. So laser defense. So I created this thing. So somebody asked me to create a computer science-y thing for a high school math course, and I came up with this, and they didn't end up using it, and so I'm giving away to you all. We do not yet have a video for this. So many typos. What's going on here? We don't have a video for this, but I'm quite proud of it. So the premise of this is that there's some sort of, like, imagine that you're at an airport and there's some drone that's traveling at a constant speed, and you are in control of a laser, and the laser is going to try to shoot down the drone so that it doesn't get sucked into like a jet engine or something like that, and so to make sure all of the passengers on all the airlines are safe. So that's the basic premise of the game, and so you've got to move the laser. But a true fact about lasers is that they come down to a focus. I mean, in principle, you can have an infinite focus, but if your laser is big enough, you might want to control whether that focus is over here or over here, and so you're trying to make sure. And the basic idea is that you can hit it with the laser all along this thing, but the highest intensity light is going to be right at that circle there. And so a lot of these laser systems are limited in how much intensity they can provide, and so you really want to try to make sure that the beam is at the peak focus, right where the object is, because sometimes all you're really trying to do is just make the tiniest little hole in this thing to shoot it down, and that's all. Like, if you can just slice off of a fin of a propeller, then that's all you need to bring one of these things down, if that makes any sense. So that's the basic idea. In practice, the game, I have to admit, in practice the game looks a lot like the missile defense game from sort of the late 80s. So that's, I'm not going to say that was an accident. It was sort of on my mind as I was building this thing. But you start off with something, here's your drone, and and it's moving, and then you have to add the code to add the laser to it, which I think I did. Where did I do that? I think I did that over here. So you add some code to is that it? Yeah. So you add some code to put a laser in it and to give arrow keys to control where this thing is going. And the basic idea is that you want to try to shoot down the drone, which is not crazy hard. And then when you shoot it down, it starts to fall down to the ground, and that's cool. And then the next thing you can do is to like try to catch it and all this stuff, because so the first part of it. So there's two parts. So the first part is just trying to make sure that you are correctly detecting whether this circle is in the vicinity of the drone. And so you do that with the Pythagorean theorem, similar to how you do it with PyDay, right? And then a fun extension to it, which is in the part 2 laser defense. So not this one, but the let's see. I think that's yeah. So in the part 2 of the laser defense, it gets a little bit more complicated. And what happens in part 2 is essentially that you want to, whoops, just a second. So you want to try to capture, so you want to try to make sure that there's, so I think I did this over here already. Did I? So the basic idea is that you have this platform that's trying to capture the drone. So once you shoot down the drone, there's a platform that captures it, and you actually, initially you control that with some keys on the keyboard. And that gets to be really annoying, essentially. So, like if you go up, yeah, so, let's see. So right now we don't have the capture thing on it, but if you follow the directions, you can add a platform. There we go. So we're shooting at it, but with other keyboard keys we can try to capture this thing. So I missed it that time, but I'm gonna try to shoot this thing down. I'm moving very slowly. All right, so moving that. No. Here we go. All right, it's gonna hit that. Boom. Move this thing. Am I gonna catch it? Yeah. So you try to move the thing to catch it, and then at this point I haven't added code yet to say like you did it, you caught the thing, but you want to catch the drone before it hits the ground. And so what's cool about that is that there's this line that defines the laser, and there's a line that defines the path of the drone, and what you can do is set these two equations equal to each other and solve for the x position, and then what you want to do is you want to set this platform at the position of the x-intercept so that you catch the drone once it's been hit. So it's a good application of trying to find the x-intercept, essentially. So that's why it's a math activity rather than a physics activity. But then you can go a step further, and you can automatically calculate that x position, or even automatically calculate what angle that this thing should be in, that the laser should be at, so that it actually automatically targets the drone. So if you notice this, I'm not touching anything on the keyboard, and this laser is just automatically targeting this drone. Right, so boom, I hit it, and now the platform is right there. So let's see. I have to hit spacebar. So there you go. So that's the fun thing. And to make sure you have the correct angle, it does take a little bit of trigonometry. And long story short, you can use the x-intercept and the y-intercept and with an arctangent function to figure out what the angle has to be. So maybe you don't want to do this unless you're teaching some serious trigonometry, but that's the basic idea. This does exist on the STEM Coding Heroku app thing if you want to check it out there. You can also check it out here. So I don't know that this is for sure data science. I mean, there is a step here where you can save the data to a table and just double check that the x-intercepts are what you expected them to be and the y-intercepts. But we made them for high school math, and yeah, we definitely hope that you like those. Cool. So there's still more activities that are like less polished that we haven't shown yet, which we can maybe talk about on Discord. But that's what I wanted to show today. The mathematical floor activity is pretty cool too, but it's similar to laser defense. It's very there's a lot of trigonometry in it, so which you can already detect from that, right? Lots of trig here. So, but it's pretty cool looking. There's all these different patterns that you can make. It's very visual. So that's fun. So this has trig, and this one has trig, and Pi Day Part 2 has trig, but often there's not a ton of trig and all this stuff. But anyway, so that's what I had to share for today. We're still building our high school data science activities. We're still building more activities for high school math. But please interact with us on Discord, and please consider joining us tomorrow on Google Meet for our sort of like, all right, summer's running out, I hate to say it, but let's get ready to teach. So thanks for tuning in, and I'll see you all some other time. Thanks.